Let's now talk about a chi-squared test for the independence of two attributes. We have over 1,000 data collected concerning the width and the length of various pins that are constructed. And we have some of them are too long, some are too short, some are too wide, some are too thin, and some are correct. Does it appear that these classifications are independent or not? This is an application of the chi-squared test. So to do this, I will do this calculation in Excel. If you don't have Excel, then the same calculation can be done by hand or using a spreadsheet program on your calculator. So we have these 3x3 table for the observed values. And let me set the format here so that everything's centered, just so I can see it easier. Okay, and let me highlight these so that we can see that this was the original number. So those are the original numbers. The next thing that we have to do is figure out the row sums and the column sums. So I need to add up the rows. So 13 plus 117 plus 4 is 134. Then filling down, I get the others. 5 plus 68 plus 8 is equal to 81. I also need to find the column sums. So adding those three numbers together, I get 80. And filling across, 4 plus 80 plus 8 is 92. And if I go one more step, I get the total number, 1,021. So what's on the screen in the yellow are the observes. The sums that you see are used to figure out the expecteds. So if I want to figure out the expected number under the assumption of independence, I would have this. So let me back up a step and let me type out carefully the null and alternative hypothesis. The null hypothesis, and let me turn off the alignment so that these will come out nicer. The null hypothesis for these problems will always be that the two attributes are independent. So classification of length and width are independent. And the alternative hypothesis would be that very modestly, that the classification of length and width are dependent. Okay, so now that I have these observed, let's figure out the expecteds. The expected in this category would be equal to this number times this number divided by this number. So the expected number in the first row, first column, would be the sum of the first column times the sum of the first row divided by the total. And to make the filling work, we will throw in the dollar signs. So I get 10.5 there, and then I clearly made a mistake, so let me fix that. As I said in class, I can never remember which way it goes, so if it doesn't look like it works, let me do this. The reason I knew it didn't work is I had a 0. That's clearly incorrect. So this time if I fill down, instead of getting a 0, I get something that's a little bit more common sense. Filling across, I get the others. So that this number here indeed will be equal to 806 times 92 divided by 1,021. So that matches what ought to happen. So those are the expecteds. Again, Excel can do this fairly quickly. If you don't have Excel, then you have to do the calculation by hand. Next, we find the chi-squared value. The chi-squared value, we need the observed minus the expected squared divided by the expected. So let me write that up here so I can see what the formula is. The chi-squared value is equal to the sum of the observeds minus the expecteds squared divided by the expecteds. Okay, so in our case, we would have a 3x3 table for each of these. So we'd have observed minus the corresponding expected squared divided by the expected. and then I would fill across to get all 9 of those terms. And so chi squared would be equal to the sum of these 9 numbers, which would be 7.462. So in our case, the test statistic is equal to 7.4605. Now, to determine if that is too big or too small, I will use the chi-squared test. In this case, I have 4 degrees of freedom, 3 minus 1 times 3 minus 1. So the number of degrees of freedom is equal to the number of rows minus 1 times the number of columns minus 1. So in this case, I have 4 degrees of freedom. So I have 2 ways of determining whether to retain or reject the null hypothesis. First, I can compute the p-value. That would be equal to chi squared dist right-tailed, using the number that we see here, 7.4605, and 4 degrees of freedom. A similar computation would work using a calculator, if your calculator is able to perform this, and so we get 0.1135. So that number is bigger than 5%, and so we would retain the null hypothesis. The other way that this could be done is to figure out the critical value. The critical value would be equal to chi square inv RT, and the alpha value is 5%, and the number of degrees of freedom is 4. And so hitting enter, we get the critical value of 9.4877. So let me draw what this picture looks like. So let me clear off a little bit of space so we can see this. So the picture would look like we have a chi-square distribution with 4 degrees of freedom. The chi-squared kind of looks like this. The critical value is 9.4877, which means that the area shaded in black is 5%. That's the alpha value that we have for this problem. So if I have a value over here to the right someplace, then I would reject the null hypothesis because that'd be the area to the right of that would be too small. On the other hand, if the test statistic falls over here to the left, then I would retain the null hypothesis. In our case, we're going to retain. The value of chi squared was 7.4605, so that falls, say, here. And so the area to the right of this green line is going to be bigger than 5%. In fact, we figured it out that the green area that's being shaded here is 11.35%. So our conclusion is that we retain the null hypothesis. And let me again turn off the, get the alignment to work so that it'll be easier to write. So we retain the null hypothesis. It appears that thickness and length are independently determined. That there's no association between, say, having a over thick versus overly long, and so on. So for these steel pins, it appears that the characterization of both thickness and length are independently determined.